Welcome to episode 63 of your CYSA Plus Prepcast. In this episode, we are turning our attention to a specialized and increasingly vital area of cybersecurity, scanning critical infrastructure systems. This includes operational technology, industrial control systems, and supervisory control and data acquisition environments. These systems form the technological backbone of our energy grids, transportation networks, manufacturing plants, and essential utilities. As a cybersecurity analyst, understanding how to safely and effectively perform vulnerability scanning in these environments is not only essential for protecting public safety and operational continuity, but is also a key competency for the CYSA Plus exam. This episode will help you understand the differences between these industrial technologies and traditional IT systems and how to assess their security posture with precision, caution, and compliance in mind. Let us begin by defining what we mean by critical infrastructure systems. These are the technologies that manage and control industrial processes essential to modern society. Operational technology refers to systems that directly monitor or control physical devices and processes. These can include systems that regulate power plants, manage water treatment facilities, control heating and ventilation systems, or coordinate production lines in manufacturing environments. Unlike IT systems, which handle data processing and communication, OT systems are directly tied to physical actions and outcomes, which makes them particularly sensitive to disruptions. Within the broader category of operational technology, we find industrial control systems. These systems are responsible for managing, automating, and monitoring industrial operations. They include distributed control systems that manage complex production processes, programmable logic controllers that execute predefined logic for equipment control, and remote terminal units that collect sensor data from field devices. Each of these technologies has its own communication protocols, security challenges, and operational constraints, all of which must be considered when planning any kind of vulnerability assessment. Supervisory control and data acquisition systems fall within the ICS umbrella and play a unique role in managing dispersed assets. SCADA systems enable centralized control and monitoring of geographically distributed infrastructure. These systems are common in energy transmission, municipal utilities, and transportation networks, where operators need to manage operations across wide areas. SCADA systems are designed for reliability and uptime, and many of them were built before cybersecurity was a design requirement. As a result, they are often highly sensitive to scanning activity, making safe and informed assessment practices especially critical. When it comes to vulnerability scanning in these environments, caution is paramount. Many of the components used in OT, ICS, and SCADA systems were not designed to withstand the probing and interrogation that are routine in IT scanning. A simple port scan or vulnerability probe that would be harmless on a typical server could cause a field controller to crash or a sensor to fail, with real-world operational consequences. In extreme cases, inappropriate scanning could cause loss of visibility or control over critical infrastructure, leading to safety incidents or regulatory violations. Because of these risks, analysts typically rely on passive detection methods when assessing critical infrastructure systems. Passive scanning involves monitoring existing network traffic, system logs, and communication behaviors without sending any probes or requests to the systems themselves. Analysts can use this information to infer vulnerabilities, detect misconfigurations, and identify anomalies without putting production systems at risk. Passive methods are the preferred approach for establishing a baseline security posture in sensitive operational environments. Passive vulnerability detection tools offer analysts real-time insight into vulnerabilities through non-intrusive observation. These tools monitor traffic flows, protocol use, and asset behaviors to detect risks without ever engaging directly with the systems. Platforms such as security, information, and event management solutions and intrusion detection systems are often deployed in these contexts. Specialized OT monitoring platforms add even more targeted capabilities, allowing analysts to detect unpatched firmware, insecure communications, and protocol deviations specific to ICS or SCADA environments. To support these needs, organizations often deploy ICS and OT-specific security tools. Solutions such as Clarity, Dragos, and Nozomi networks are purpose-built to provide visibility into industrial environments without disrupting operations. These tools are equipped to understand the proprietary protocols, unique architectures, and operational dependencies that define industrial systems. Their scanning and monitoring capabilities are finely tuned to detect threats safely, making them an indispensable part of any critical infrastructure cybersecurity strategy. Effective scanning in these environments requires extensive coordination. Cybersecurity analysts must work closely with plant operators, control engineers, and maintenance personnel. Unlike traditional enterprise scanning, vulnerability assessments in ICS and SCADA environments cannot be conducted independently. Analysts must communicate scanning objectives, review system interdependencies, and confirm acceptable windows for data collection or interaction. This collaboration ensures that assessments are performed with full awareness of operational constraints and that any actions taken are consistent with safety and continuity goals. In addition to technical and operational considerations, compliance is a major driver of vulnerability assessment in critical infrastructure. Sectors such as energy and water utilities are governed by regulatory frameworks that define how and when systems must be assessed for security. For example, the North American Electric Reliability Corporation's Critical Infrastructure Protection Standards specify requirements for risk assessments, scanning methodologies, and documentation practices. Analysts must ensure that their scanning practices align with these rules, both to maintain compliance and to demonstrate due diligence in protecting essential services. For more cyber-related content and books, please check out cyberauthor.me. Also, there are more security courses on cybersecurity and more at baremetalcyber.com. Let us now explore best practices and safe scanning techniques specific to operational technology, industrial control systems, and SCADA environments. While passive methods are generally preferred, there are scenarios where active scanning may still be necessary. In these cases, analysts take extreme precautions. Active scans are only performed when operational risk is acceptable and typically only during scheduled maintenance windows. These scans are coordinated with engineering teams, and every step is supervised to prevent disruption. Analysts limit the scope of scans to predefined systems and use the least intrusive settings possible to gather only the information needed. To support safe active scanning, analysts use tools specifically designed for ICS and OT systems. These tools include protocols and scanning engines that are aware of how industrial devices behave. For example, they know how to interact with programmable logic controllers and remote terminal units without overwhelming them. The goal is to retrieve vulnerability data without triggering faults, resets, or alerts. Specialized tools reduce the risk of operational interruption, which is why analysts avoid using general-purpose IT scanning tools in industrial environments unless the environment is segmented and isolated. Segmentation plays a critical role in minimizing scanning risk. Analysts work with network engineers to ensure that critical OT environments are logically and physically segmented from IT networks. This segmentation not only supports defense in depth, but also allows scanning to be tightly controlled and scoped. If active scanning is required, segmentation limits the exposure zone, reducing the number of systems affected and containing potential performance impact. Segmentation also makes it easier to identify which systems are in scope for scanning and which require special handling. Another important best practice is to test scanning procedures in controlled environments before applying them in production. Many organizations maintain lab environments that mirror the configuration of their ICS and SCADA systems. Analysts use these test beds to validate that scanning tools are compatible with the deployed systems and that their configurations do not trigger failures. These test environments provide valuable feedback that allows analysts to adjust scanning parameters, ensure safety, and gain approval from operations staff before scanning real infrastructure. Maintaining a detailed asset inventory is fundamental to successful vulnerability management in critical infrastructure. Analysts document every component in the OT environment, including controllers, firmware versions, protocols in use, and interconnections. This documentation allows for precise targeting of scans, helping analysts focus on high-risk assets and avoid systems that are unstable or unsupported. A strong asset inventory also helps in prioritizing remediation efforts, correlating vulnerabilities with operational importance, and ensuring full visibility of the environment. Patch management in industrial systems is particularly challenging. Many OT devices have limited update capabilities or require vendor-specific firmware updates that cannot be applied without system downtime. Analysts coordinate closely with engineering teams to determine when patches can be safely applied and whether compensating controls are needed in the meantime. Prioritization is based on severity, exploitability, and the potential impact of disruption. In many cases, patches must be tested in lab environments before being rolled out to production systems, and all changes must be documented and reviewed. Continuous monitoring provides another layer of visibility without requiring active scanning. Analysts implement passive monitoring solutions that provide alerts for unusual behavior, configuration drift, or unauthorized communication attempts. These tools are often integrated with centralized logging platforms, allowing analysts to correlate events across systems and respond to signs of compromise quickly. Continuous monitoring supports both vulnerability detection and incident response, and it can operate with minimal disruption to ongoing operations. Threat intelligence tailored to OT environments further enhances scanning and monitoring effectiveness. Analysts subscribe to ICS-specific intelligence feeds that report on vulnerabilities affecting control systems, observed threat actor behaviors, and ongoing campaigns targeting industrial sectors. These feeds help analysts contextualize scan findings and identify which vulnerabilities are most likely to be targeted. By integrating this intelligence into scanning tools and monitoring systems, analysts improve detection accuracy and focus remediation efforts on the most relevant threats. Documentation remains a cornerstone of effective vulnerability management in critical infrastructure. Analysts maintain comprehensive records of scanning procedures, schedules, exceptions, findings, and remediation efforts. Documentation includes risk assessments conducted before scans, communication logs with operations teams, and follow-up evaluations after scanning activity. These records support regulatory compliance, demonstrate responsible scanning practices, and provide institutional memory that benefits long-term cybersecurity strategy. Detailed records are particularly important in industrial settings where changes are tightly controlled and system stability is critical. Finally, continuous training ensures that analysts remain effective in these specialized environments. Industrial systems differ significantly from traditional IT infrastructure, and analysts must understand the technologies, protocols, and operational constraints that define them. Training includes hands-on experience with ICS components, safe scanning techniques, regulatory standards, and passive monitoring technologies. By staying current with emerging threats, tool capabilities, and industry best practices, analysts build the confidence and competence needed to secure critical infrastructure without compromising operational safety. To summarize Episode 63, scanning critical infrastructure systems such as OT, ICS, and SCADA requires a cautious, informed, and highly coordinated approach. These environments cannot be treated like traditional IT systems. Analysts must rely on passive methods when possible, use specialized tools when active scans are necessary, and always prioritize safety and uptime. Working closely with engineers, maintaining strong documentation, and following industry regulations ensures that vulnerability management efforts support both cybersecurity goals and operational requirements. These skills are essential for success on the CySA Plus exam and even more critical when protecting the infrastructure that modern society depends on. Stay tuned as we continue your comprehensive journey towards CySA Plus certification success. Thanks for listening. To learn more about cybersecurity, please visit baremetalcyber.com. There you will find best-selling books, videos, and even more free cybersecurity training courses. Please subscribe to the Prepcast and our various podcasts. And thanks for listening.